Okay, we continue with harmonics in the IPS, right? So as what you can see here, the illustration here show you some waveforms with the third harmonic and the fifth harmonics, and as well as the resulting waveforms due to the combinations of the fundamental, third harmonics and the fifth harmonics. Okay, as you can see in the red color, this is the resulting waveforms. It's due to the summations of the fundamental, third harmonic and the fifth harmonics. And of course here you will have the fundamentals for the green color. So this is a pure sinusoidal waveform. Okay? No matter it is a voltage or current, so it is in the sinusoidal, a pure sinusoidal. And we will have the third harmonics, which is with the frequency 150 hertz in the blue color, and as well as the fifth harmonics. Fifth harmonics with the harmonics with the frequency of 250 hertz. So you can see it is narrower. Is the narrower as compared to the third harmonics. Okay, this is what we are going to explore in a few minutes more. Okay. And we also have learned a little bit on the THD, the percentage of the total harmonic distortions in the power factor corrections. Okay. So you can know that the total harmonics distortions percentage is representing how much is the harmonic contents or harmonics components that available in our systems. In our systems, with regards that we just take the calculation on the harmonics and not include the fundamental. So this is 100% means is the fundamental if we are operating at a 50 hertz. Okay, so 50 hertz will be our fundamental waveforms. Okay, so this is the magnitude for the fundamental, and of course for the THD, so we start from the second one, and the second one, which is second order harmonics, third order harmonic, and etc. So in the frequency, it is represented by 100 hertz, 150 hertz, and etc. Okay, so the THD, as we understood, there's two THD. One is for the voltage and another one for the currents. So all the calculation is using the same equations. I mean, we just sums all the harmonics components, and then we square it, and then we compare with the fundamentals. Then we multiply with 100%, then we get the percentage of the total harmonic distortions. Okay, of course in the harmonics we are dealing with the frequency. The frequency is our main, and with that we need to represent, and I mean we have to analyze our waveforms, the waveform that we obtain or we capture from the power, maybe the power quality analyzer, using the Fourier series. And the Fourier series will look like this. This is a very basic fundamentals. Y is the total, the resulting waveforms. I mean the total waveforms, and the capital Y naught here, this is the DC components. Generally it is zero. It is zero. It is a zero in the general, unless you have the special conditions, then it just exceeds this one. Especially in the imbalance conditions, then you need to consider the DC components. Otherwise it is always zero. It is always cancel out to each other, positive and the negative parts of the waveform. And regarding to this one, so this is the summation. As you can see, the number is from 1 which is the fundamental. So we count from fundamental until the infinity. Infinity in this case. So yn is the RMS value for either voltage or currents. It is RMS value. So bear in mind, it is always a RMS value for harmonics content as well as the fundamental. So if n is equal to 1, of course it is the fundamental, and it's more than 1, which is larger than 1, 2, 3, 4, and etc. So it is representing the harmonic components, right? So it is a sine wave, and this is the number. So we start with 1, and omega is a 2 pi f. Okay, so this is representing the time series. okay, or time domain, okay, in the time domain. And theta is the phase angle of the harmonic components. As we have one example in the power factor corrections that you can see, you can refer back. So each harmonic content, for example, third order of harmonics, it has the magnitudes as well as the angles. So for example, in the voltage, okay, then we say the voltage third order harmonics is let's say 15 volts, 15 volts with the angle is minus 21, for example. Okay. So that means this angle could be positive or could be negative. It depends on the nature of the waveform or the loads that representing the harmonics. Okay. And if follow the IEC standards, whatever harmonics above 40, then we can neglect it, because above 40, that means the harmonics content, especially the magnitudes, is very small, and it won't give the significant impact to our industrial power system. So that's why above 40 we neglect. So normally we just take the counting of the harmonic from the second up to 39 only. Okay, so that is the IEC standards, right? As well as the IEEE also using implement the same things. And we need to understand where the harmonics is come from. In the IPS, harmonic is due to the switchings. It is, if you have the switching activity, then it will have the harmonics content. Okay? Because the switching is not in the 50 hertz. Normally the switching is in the higher frequency. Say let's say 100 kilohertz, 500 kilohertz, and etc. Okay, these switching elements is such as the statics converter. So you have the rectifier, you have the inverter. So it depends on your rectifier or inverter. So how many pulse you have. Okay, P representing the pulse. So let's say you have 6 pulse, 6 pulse of the rectifier. So if you have operating your 6 pulse rectifier in the IPS, that means this is representing the harmonics, the harmonics available. So that means if 6 means K is begins with from 1. So if K is equal to 1 multiplied with 6, that means this is 6 plus minus 1. So that means your harmonic contents from the 6 pulse rectifier or inverter is the 5, because it's minus 1. 6 minus 1 is 5, and then another one is 6 plus 1, it's 7. Okay, that means it is 5th harmonic and 7 harmonics, which is the lowest one. So it is impossible to have a third order harmonics and etc. Okay, in this case. And if we keep increasing the K, so if the K we increase to 2, so I mean 2 times 6, because we have 6 pulse, 2 times 6 is 12. 12 plus minus 1, that means another upgrading harmonic content will be 11 and 13. Okay, 11 and 13. So that we can expect if you have the 6 pulse rectifier or converter in general, so 6 pulse, then you can have a minimum harmonic content of 5, 7, 11, 13, and etc. Okay, so it depends on the multiplication of the K here, right? And another one is the arc furnace. Arc furnaces also will contribute a lot of the harmonic contents, especially when you deal with the arc furnace that control by the controller, then it will have a lot of the harmonic contents that comes from the arc furnace here. And lighting, especially if you are using the discharge lamp, as what we are normally see in the in our production line, the discharge lamp or the fluorescent lamps, then it will produce especially the third order harmonics, which is the unwanted harmonics, because this third order of harmonics, it will penetrate into our neutral system. which is very dangerous, neutral systems. And the rest of the harmonics, let's say fifth order, seventh order, and etc., it won't disturb your neutral. It just penetrate into the live wire, or the live cables. So only the third order of the harmonic will penetrate into our neutral. So it will give wrong information or wrong signal, especially to our protective device. Especially if you are dealing with the RCCB, for example, the residual current circuit breaker. So it will, RCCB is operating according to the residual currents detections between the live and the neutral. So for example, if you have the third order harmonics entering your neutral, for example, so your neutral having some amounts of the the waveforms or the magnitudes, for example voltage, and then, or the current, the current in this case, it is dealing with the current because RCCB. So when you have a little bit third order harmonic content of the current in the neutral, then this RCCB will detect, and there is the difference. There is the difference between live and the neutral, because in the healthy condition, live will be back to the neutral, and live will be back to the neutral. That means in the healthy condition, live is always equal to the neutrals. So in that case, the RCCB will, it might be tripped. It might be tripped due to the difference between the live and the neutrals contents. So that is one of the disadvantage of the harmonics. It will disturb the protective devices. Another ones, no doubt, we will have the harmonic content from our variable speed drives. Our variable speed drive, no matter you vary your frequency or you vary directly the voltage, so you will have to use the converter. Once you use the converter, then you will have the switching element, the switching elements. So with that, it will provide the harmonics contents in our industrial power systems. And the last one is the welding machine. So this is not the all the harmonic sources. This is some of the significant harmonic sources from the IPS. So the welding also will play quite important roles in the harmonics generation in our industrial power system. Okay, so this is one of the most common harmonic source, is the rectifier loads. As I told you just now, so it much depends on how many pulse you have. So let's say you have 6 pulse, that means you will have 5, 7, 11, 13, and etc. Alright, it is using the 1/h rules. So H is the harmonics order that we wanted to find. Okay, let's say we can find the fundamental currents. Let's say the fundamental current is 100 ampere. Then we can simply use this 1/h rule to find what is the, let's say for example, we wanted to find a 5th order harmonics of the current. So we can use 1/5 multiply with the fundamental, the I1, which is the 100, for example, in that case. Okay, so 1/5 times 100, that means we can expect the 5th order harmonics currents is 100 divided by 5, which is 20 ampere in that case. So this is how the 1/h rules plays. Okay, so this is the meaning. That means in order to find the 1/h rules, of course we need to identify what is the fundamental. What is the fundamental? No matter is the voltage or current, it is used the same rules. Okay. And this is one of the examples using the 1/h rules. So let's say we have 1 MVA or 1000 kVA, 6 pulse rectifier. So it serves 2 kV of the DC loads. So that means that the DC load is operating at 2 kV DC, right? And then this voltage is consistent over all loads in the range of 100 kilowatt to 250 kilowatts. That means it's using the delay angles to adjust so that the DC voltage is always consistent. It's always consistent from the range of 100 to 250 kilowatts. Okay? So this is our DC loads, and we have the supply transformer as well. So that this transformer is rated at 1100 kVA, 13.8 at the primary kV, and at the secondary it is 6900 volts. Okay? With the reactant or the impedance as a whole is 20%. That is operating at 50 Hertz. That means we can use the 1 over H rules to find and to identify what is the fifth and the seventh order of the harmonic the current contents in our system here. Okay? So what we need to find is at the high voltage side, and the high voltage side means is at the 13.8 kV here. It's not at 6900. Okay? So of course 6900 is connected to our loads, but our intention is to find the incoming harmonic contents of the currents. Okay? So when we that means we vary our DC load from 100 kilowatt to 250 kilowatt operating. So let's say the solution is like this one, and of course you need to find the transformer reactance first. So X is equal to V square over S, and this is very common. X is equal to V square over S. Then this is to find the impedance base. So we start from the secondary. Why we start from secondary? Because our load is at the secondary sides. Okay, so that's why we need to start with the secondary voltage here, and then 6900 volts square divided by transformer ratings. Then we obtain for it 3.28 ohm, and then we try to find what is the Xs. The Xs of the transformer is given as 20%, so 0.2 in per unit multiplied with the X base. Okay, then we get 8.65 ohms. And then these are the 6 pulse rectifier formula. I mean, you don't need to remember the formula. Okay, so you can refer to this anytime, no matter it is in the test or in the final exam. So you can refer back to the slide. Okay, so the VDC is this one, and then we just substitute the value that we have. Okay? And this is to find the power factor for the displacement power factor. It is not the true power factor, but rather it is a displacement power factor. It's about the cos alpha plus the mu divided by 2. Okay? Of course, the mu we need to find it from here first. And we just substitute the voltage is 2 kV, the DC, and then we just substitute this is at the secondary of the transformer voltage 6900, and then what else we have? This one is the ACK, the transformer ACK here. So this is what we vary. That means we start from 250 kilowatt of the DC loads. Okay, 250 kilowatt of the DC loads, and then we divide by 2000 because this is the voltage and the DC voltage. And then once you solve this one, you can obtain the alpha is equal to 71 degree. And of course from this one, this formula, you can find the mu later on. You can find the mu. So all in here, then you can have the mu is 13.04, and of course you can find the power factor after that. The power factor, the displacement power factor is 0.216 only. It's very low. Then we will find the S, and the S in order to find the currents. Okay, so the S is the with the 250 kilowatts. Of course, our load is 250 kilowatt divided by the the power factor, the displacement power factor, which is 1157 kVA only. Okay, with that we can find what is the I1. The I1. So the I1 is at the fundamental. This is the fundamental currents, and the fundamental currents. So which is 48.4 ampere. 48.4 ampere here. And the I5, this is how we play the rules. 1/5, because we need to find the fifth order of the harmonics. 1/5 times the fundamental. So we can expect our fifth order harmonic is 9.68 ampere. And seventh order of harmonics also 1/7. This is about 6.92. And we twist our DC now to 100 kilowatt, and you can use the same procedure and the calculations to find the fifth order and the seventh order harmonics with using the 1/h rules. So this is a summary of the harmonic content, the fifth order harmonic content, seventh order harmonic content when we adjust our DC loads to 250 kilowatts, and this is for 100 kilowatt case. Okay? So you can see the harmonic content is gradually lower from fifth to seventh. Okay? So this is the nature of the harmonics. And in terms of the consequences, and I mean the effects of the harmonics to our IPS, basically we can divide this effect into two. One is the instant effect, and another one is the long-term effects. Okay, so we check for the instant effect first, instantaneous effects. So of course it will disturb the controller with the harmonic contents. So normally it's the voltage or the currents. So of course, if currents, that means once you add in the harmonic contents, your current will be higher, and the waveform is no longer sine wave, and no longer 50 hertz of the sine wave. So it is the disturbed. So we can call it the distorted waveform. Then with the distorted waveform, so if we use the a controller, let's say we are not using the AI based controller, we just use let's say the PID controller or the fuzzy controller, so it might read the signal differently. So that means it will disturb the controller. So you can imagine, once your controller has been disturbed by this harmonic content, so what will be the next effects to your production line. Okay, so the production line will have I think it's quite messy, or the chaotic conditions happens after that. Okay, and then the second instant effects of the harmonic content is additional error in the induction disk. So this one is for the old method of the kilowatt hour metering. So nowadays I think we don't use the induction disk already. Okay, so all become the digital. The digital meter, it won't give any impact on this one. Okay, unless the components in the meter, the digital meter is sensitive on the harmonics, then yes, so it will read wrong. That means the measurements, the wrong measurements. And of course, as I illustrates to you just now, if you are having the RCCB, especially you have the third order harmonic, then it will disturb your protective devices. It is not only third order harmonics. So it depends on which type of the protective devices that you use. For example, if you use the overload protective devices, let's say using the thermal, and I mean the thermal based protective devices. So let's say you set at let's say 115%. I mean you have extra 15% of the overload. So with the harmonic contents, so because the harmonic contents, one of the harmonic contents effect is they will add in the power losses. For example, let's say the power supposedly is 100. So with the harmonic content, it might be 120 already. It might be 120 watts. So if we tune our protective devices, overload protective devices at 15% extra, so that means now we have 20% extra. So our protective devices will act very fast. It will respond very fast, saying that there is a over voltage, but by right it is not the over voltage, it is just a normal condition with the harmonized conditions. Okay? And for the long-term effects, of course, with the increments of the currents, so it will have the additional heatings at the inductive load or in the equipment, especially for the cables. So of course, in for with this additional heating in our equipments, for example in cables, so it will shorten the lifespan of the cables. So this is one of the example for the cable. So we have plenty of the equipment that might be affected by the harmonic. For example, the winding in the transformer, for example. Okay, so it will also give impacts to that. And of course, with the variations of the sinusoidal waveforms, from the 50 hertz to you can count the harmonic content. That means with the harmonic contents waveforms, so that means it will have seems like the vibration and noise, especially the audible noise when you're operating the induction motor with the harmonics content. Okay? So you will have that, so because your voltage and current has been disturbed by the harmonics, and it is no more the sinusoidal pure sinusoidal waveforms. Of course, when you zoom in the harmonized waveforms, then you will have a lot of the a different range of the frequency waveform. Then with that, it will make the audible noise and the vibrations to the induction motor. And of course, with the harmonic content also, it will give the impact, the long-term impact to the let's say the EMI, electromagnetic interference, to the communication and control circuit as well. And these are some of the symptoms by the harmonic content. You can read through it, including the nuisance trips, and the motor vibrations, and the malfunctionings of the generator regulator. Okay, now we look at the IEC standard, and this is the IEC standards that's representing the various classes. We have 3 classes of the devices or equipments represented by the IEC. So that we have class 1, class 2, and class 3. Okay. So as you can see, this is the nominal voltage and the voltage tolerance allowable for class 1 is plus minus 8%, class 2 10%, and class 3 is 10 to 15%. Okay, so with that you can estimate so which one is more sensitive to harmonics. Okay, with the harmonic contents, when we add in the harmonic contents to our fundamental waveform, so of course the magnitude, no matter is the voltage or current, will be increased. In this case, it is more to the voltage. So that means it will increase the voltage magnitude. So from here you can estimate class 1, class 2, and class 3, which one is more sensitive to the harmonics. Okay, so of course this one will be more sensitive to the harmonic, because it has a lowest tolerance. So it's only 8% as compared to the class C here. So that's why the class 1's device or equipment is normally protected by the earth, because it is very sensitive to the disturbance. And for the class 2, normally it will have the double installations, especially at the PCC, point of common coupling, and the IPC, the internal point of coupling, And for the third class is normally for the low voltage, and the LV here is the low voltage. So this is supplied from the separate, and this is the separate a low voltage, and separate low voltage power source. Okay? And you can see the voltage unbalance. This voltage unbalance is different than the harmonics. Voltage unbalance is defined by the voltage of the negative sequence divided by the voltage at the positive sequence. So they mean the negative sequence and the positive sequence have some difference. So this is so-called the voltage unbalance. So for the voltage unbalance, the class 1 is 2%, and 2 as well. Class 2 as well is 2%, but class 3 is allowed up to 3%. And this is the frequency, that means the power supply frequency deviations. So all the way is plus minus 1 hertz, 1 hertz. So unless you have the isolated network, if you have the isolated network, that means you are not connected to the grid system of the TMB, for example. So the allowable frequency deviation is plus minus 2 hertz, because when you have this kind of the lower or a little bit increments of the frequency, it won't disturb the rest of the customer or the consumer. Okay? And now we move on to the harmonic contents and the standards for the IEC and the harmonic content. So normally we just take up to here is give you until 49, 49 maximum order. Okay? The fifth order is for class 1, 2 and 3, so you can refer it. Okay? So the minimum is 2, is 2 at order of 17. So of course it will gradually reducing here. Okay? From this is the low order harmonics. Low order harmonic is 3, let's say, so 17 is 2 only. Okay? So for class 3, of course it is higher than class 1 and 2, so it's 8% up to 4% at the order of the 17s here. And same to the odd number, the odd number of the harmonics, the odd number of the harmonic with the multiple of 3. So this is the multiplication of 3. So this is a so-called the triplet harmonics. We call it a triplet harmonics, a third order harmonic, 9 order harmonic, 15, and etc. So this is quite dangerous to our neutral system. And the even number of harmonics, this is not that rare. It is not that common. It is quite rare case. It's not as common as the odd number, and the even number is let's say 2, 4, 6, 8, and etc. So this is quite a rare case of the harmonic contents, but it is quite dangerous because it will cause the resonance. It will cause the resonant effects especially. So that's why the allowable percentage is much lower as compared to the odd number of the harmonics. And this is the total harmonic distortions percentage. The 5% for class 1 and 10% for class 3 as well. So how to mitigate the harmonics? We only can mitigate or reduce the harmonics, so we cannot eliminate it totally. And I mean the harmonic content cannot be totally eliminated from our IPS. We only can mitigate or reduce it. So some of the methods of the harmonic mitigations are the passive filter, or we call it as a tune filter. That means we tune to a specific order of the harmonic. For example, we tune to 13 order of the harmonics, because the 13 order harmonic is the highest one, for example. Okay, so this is the tune filter. And another one, we use the advanced power electronics concepts, which is the active filter. Active filter, that means we have the controller, we have the that means this is the closed loop system, the closed loop system. And Another one, if you don't have this one, if we don't have the filter, then we can directly purchase the multi-pulse transformer as well as the HMT here. HMT is the harmonic mitigation transformer. So of course it is more costly as compared to the same size of the transformer, the common transformer. So this is the passive filter, the passive filter. So normally it is connected in in parallels like this one. You have the normally R, so you have the XC and the XL. Okay? So for example, here we have the tune filter. So you have the R components and the capacitance components and the reactance components here, and the L inductance components. And why we call it as a tune? Because let's say for example here, so you can see this one is the harmonics order. The harmonic order from 1, of course 1 is the highest, 100% here, hundreds. This is the impedance. This is the impedance of this, the impedance of this. So if we work it properly and we design it properly, that means we can tune it, you see. So in this case it tuned at 11. So that means we tune it to 11 order of the harmonic. That means we try to reduce the 11 order of the harmonic in this case. Okay, so how to calculate or how to design this is pretty simple. So this is the harmonic contents. Of course it is the frequency of the harmonics divided by the fundamental, let's say 50 hertz here, and it is equal to the square root of the XC divided by XL here, XC and XL. And of course you can that means you can just leave it as the LC only, and the LC with considering the 2 pi f. F of course is the fundamental frequency here, and the XC, so XC also equivalent to the kV square over Q. Q is the either the kVAR, normally is the kVAR or VAR. That means the reactive power rating for the capacitance, the capacitance. And R is related to the Xn divided by Q, which is Xn is the XL multiplied with XC, and then we square root it, and we square root it. So what is the Q? Q actually is the quality factor. Q is the quality factor. So quality factor means is the sharpness of our tuning, the sharpness of our tuning. Okay, so as you can see here, the tune filter normally having the Q, they mean the quality factor around 10 to 100. But for the high pass filter, so it is much lower. It is 0.5 to 5 only. So they mean what you can learn from here is if you have lower Q, for example here, so they mean you tune at the lower order of the harmonics, lower order of the harmonic or lower frequency. Because the high pass filter, we only can let the higher order of the harmonic. Let's say the high pass filter, let's say we tune it at the 11 here. So that means those harmonic order more than 11, then we can that means we can let go. That means we can make it pass to the systems. And below 11, that means we just filter it. So that is the high pass filter. So that's why it just tuned at the lower frequency or lower order of the harmonics. Okay? And this is the impedance. This is the impedance. I mean the total here. The total here. And this impedance is very important. That means when you plot the graph, you plot the graph versus the frequency especially, then you can see how much is the ZECs perform, how much is the ZEC perform. So that means where it tuned. For example, in this case it's tuned at 11 order of the harmonics, right? Okay, we have one example here. So 4.5, so you have a series filter is tuned to 11's harmonics, and then it gives us the XC is 405 ohms, and we need to calculate how much is the filter elements. The filter elements mean what is the C, what is the L, and what is the R. What is the C, L, and R values. So of course it gives us the quality factor Q as 50 in this case. So very quickly you can use those formula. So you can find the XC. So it's given 405. It is equal to 1 over omega naught C. So it's 2 pi F. F is 50 hertz and C. So you can very quickly you can find the C here. And further you can find the H. H is we tune at 11. 11 harmonic. So H is 11, and of course H is 1 over omega LC. So once we obtain the C here, then we substitute into here, and of course we can find the L very easily here. And finally with the Q and the ACN that we obtain, and the ACN actually is the square root of L over C from here also. So then we divide by Q is 50, then of course we can find the R. So you can have some exercises here, so you can try your understandings by solving the example 4.6. So what is the tuning order and the quality factor? So what is the tuning order of the harmonics and the Q value? If you have 36 kV series tune filter with XC is 544.5, XL 4.5, and R is 0.825. So I will give you the answer. So the answer for the tuning order is 11. And the quality factor is 60. So 60. So you can try yourself, and then to find the answer for the tuning order and the Q here. Okay, the active filter actually it is utilizing the power electronic concepts. And the power electronic concepts, that means let's say you have the load currents like this one. You have the load currents like this one, and then we try to reduce, and this is the harmonics. This is the harmonics that we don't want. This is the harmonic that we want, starting from the second one. This is of course the fundamental. We don't touch for the fundamental. So the second one until the rest of the harmonic content. So we try to eliminate it, or we try to mitigate it. So that's why we need to design the active filter so that it won't tune at the first one. The first one have nothing, but start from the second one, so it will anti. It's some sort like it will opposite. That means we need to generate the opposite waveform, the opposite waveform of the second, the third, and the fourth, and etc., so that it will give the minimum value. At the end we will have the clear currents like this one. We only left the fundamental, right? And then if you have the a simple industrial power system here, so you have the source currents, and the source current is very nice. It is the sinusoidal waveforms, and suddenly you have the compensator currents, and this is from the so-called the active filter, the active filter. So when we combine the IF and the IH here, so you will have the load current like this one. So our load current will like this one. So it is almost like the pure sinusoidal, but it still has a little bit of the disturbance here. And the multi-pulse transformer. So the multi-pulse transformer could be running at the 6 pulse or 12 pulse or 18 pulse or 24 pulse, and etc. So the common one is 6 pulse or 12 pulse. So the 6 pulse for one leg of the 3 phase, 6 pulse. Another legs for the 3 phase is a 12 pulse. right? So the concept is still remaining the same as the converter, which is the order of the harmonics is depending on the value of the pulse. Okay? So you have 12 pulse, that means your k is equal to 1 multiplied with 12 plus minus 1. So that means it can eliminate those harmonics with this one. And another one is the HMT. HMT is the harmonic mitigation transformer. So this is most expensive, I think. This is the most expensive transformer. You have this kind of the functions, but anyhow, this kind of the transformer is not for the high voltage. So it is only for the lower voltage or lower power applications. And normally it's just up to, let's say, 25 kVA of the application. It's more than that, you cannot use this one. Of course, you have to select, or you have to choose the filter, the filter, either the tune filter or the active filter. So this is for the smaller power application that you can use for HMT. So how it reacts to mitigate the harmonic is they use the phase shift. And the phase shift, and of course here you have the delta connection and the star connection here. So they just play with this one, and then it will tune the flux. It will tune the flux accordingly, and after that it will combine with the source impedance here, and to mitigate certain amount of the harmonics, certain amounts. But this one is only applicable up to, let's say, 30 degrees Celsius of the tuning and the phase tuning. 30 degrees Celsius only, 30 degree only. Okay. This one is we can see the comparison. Let us see the comparison. So the first one is the series. The series connected. The series connected, you have the AHC is the active harmonic conditioner, which is active filter. So the second one is the shunt hybrids, and the third one is the parallel hybrids. You have two parallels. One is the passive, one is the active, which is operating in parallel. And next is the parallel series. The parallel series means the passive filter and the active filter is running at the series, and these combinations of the filter are connected in parallel to our system. So that's why it is called as a parallel series. And another one is the series parallel types. The series parallel type, that means active filter is connected in series, but the passive filter is in the parallel. Okay. And you can see the performance, and this is some of the performance. For example, we see the active harmonic conditioner size. Okay, active harmonic conditioner size. Okay, for this series is fundamental plus harmonics, and this one is only for harmonics only. Okay, harmonics only. So that means fundamental, that means it will also eliminate the incomings. It will also eliminate the or mitigate the harmonics from the incoming. Okay, but this one for harmonics only, that means it won't treat your incoming supply. It won't treat your incoming supply. It only treat for the harmonic content from the loads. Okay. Alright, I think that's all for the harmonic contents, and now we jump into the voltage sacks and the voltage sacks analysis, or sometimes we call it as a voltage dip analysis. So the voltage dips, as you understand, it is the reductions of the voltage level, or the voltage magnitudes below 90%, below 90%. As you can see here, so we have from 0 to 110%. So this is our normal operating voltage, operating from 90 to 110%, 90 to 110%. So we call it as a normal operating. So if above 110, that means more than 10% increment, so it is a voltage swell. And below the 90%, up to 10% here, so that means 10 to 90%, it is a voltage dips or the voltage sag. So this voltage sag is divided into three categories. The first one is the instantaneous, second one is the momentary, and the third one is the temporary. And of course these three, the combination of these three voltage dips can be varied from half a cycle. That means the time range can be range from 0.5 cycle to 1 minute. 0.5 cycle means 1 over 50, for example. If we are using 50 hertz, 1 over 50 times 0.5. Okay, then you can calculate for the how many what is the times for the half cycle. So it is 0.01, is 0.01. And above the this, that means for the long term, that means above 1 minute, no matter it is a voltage swell or voltage dip. If it is more than 1 minute, we categorize it as a over voltage or under voltage, if it's more than 1 minute. So this is the definitions. Okay, the voltage sag is normally is due to the what you can see here is the sudden decrements of the Q. Q is the reactive power. Okay, sudden decrement of the reactive power. That means for example, you start your very large motor, it is more than 300 horsepower, so that means it will pull, that means it need to use a lot of the reactive power to form the electromagnetics, and that means to electromagnetic and to form the flux. So that's why when you start the large motor, or normally is for the induction motor, normally for the induction motor for the IPS, and that means it draw a lot of the Q, so with that you can expect that the voltage sag will happen during that moment. So the main cause of the voltage sag is the one, of course, is the faults. So if you have, let's say, 2 section or 3 section in your IPS, so one of the section having the faults, and another two neighboring system will experiencing the voltage sags if you have the a strong system, otherwise it will collapse as well. And for the transformer energizing also, when you energize and especially energize the transformer, also it will give the voltage sags to the rest of the system in the IPS. And the switching for the heavy loads, especially the large motor, also will contribute to the voltage sag in the IPS. Okay, so 3 types of voltage sags: single phase, phase to phase, and the 3 phase. It seems like the fault, you have the single phase, phase to phase, and the 3 phase sags. And for the single phase, it is very common. It's more than 70% of the voltage sags happens in the IPS is due to the single phase. So the single phase. So single phase is normally is due to one of the phase having the sags, because if we look at our installations in the IPS, even though we have 3 phases, but especially for the single phase loads, so we still connected phase to phase. That means from R, Y, and B, for example, R, Y, B. And these each phases will have different types of the loads, and then with the single phase loads. So if one of the phase is having problem, let's say fault, then it will give the voltage sags. It will give the voltage sags to the rest of the neighboring system. And the phase to phase voltage sags. So phase to phase voltage sags is normally caused by the, let's say you have the tree branches fall down, or or the bad weather is due to the heavy rains, for example. You will make your systems damage, then you might have the phase to phase voltage sags. It's about the faults. It's about the fault, but we can say it is just a partial fault. It is not totally go to ground, but it is a partial fault. It's a partial fault, then the voltage sag will happen. So if totally go to ground, that means that is the phase to ground fault. But it won't it won't up to the that level, right? It won't up to the totally grounded. And the three-phase sex is not that common, but even though like that, it happens when we that mean we have operating a third, that mean the three-phase equipment, or the three-phase devices. For example, you have the circuit breaker, you have the switches, you have the recloser, so all is running at the three-phase basis. Then it might have the voltage sex, and especially for the starting of the large motor here. And the most common effects of the voltage sex is, of course, when your voltage is reducing, and when your voltage is reducing, so you can experience that, or you can expect that your current will increase, in order to top up the power that is required by our loads, so the current will increase. So with the increment of the currents, a lot of things will happen. For example, you have the metering system problems, the accuracy problems, and you have motor drive effects. Then if you have the PLC also, will it will operate, that means wrongly, because the PLC is one of the voltage sensitive devices. So it depends on how sensitive is your devices to the voltage. So the more sensitive your voltage, your devices to the voltage, that means the impact is higher, right? Okay, how to calculate? It's very simple to calculate the voltage sex. That mean you have the incoming here, so you have the impedance from the source. The ZS is the impedance of the source. You have the PCC, point of common coupling, and then you drag a cable or relate the cable to the load here, and suddenly you will have the faults. You have the fault, for example, here. Then you have, of course, the impedance along the way from the PCC to the fault point here. And what we can calculate the voltage at the PCC is the some sort like the voltage divider. So we take the ZF here, divide by the total Z, and the total impedance. That means ZS plus ZF here, and multiply with the incoming supply voltage. Then we can estimate how much is the voltage left here, and with that you can simply calculate how much is the voltage dip, how many percent is there. So the industrial customer normally invest a lot, we know that, but due to improper treatment of the voltage sex, they might reduce the value of their investment. It's due to the voltage sex. And because a lot of things might happen due to the voltage sex. So with that, in order to maintain the investment value, especially for the investor that invests in the IPS, the factory, so they have to have the replacement of the components which is not that sensitive to the voltage. So that is one of the effective way. That means you can change the existing voltage sensitive devices or equipment to the less voltage sensitive equipment. Or another one is you can have more significant protections against the voltage sex. So that is two way to reduce the voltage sex in that case. And how to analyze the voltage sex in the IPS? Of course, first we need to understand our equipments. What equipment is affected? What equipment is affected? And we try to find as well the voltage sex magnitude. So how much is the voltage sex magnitude? And that means we need to determine the frequency as well. So the durations of the voltage sex. And after that, we try to install the metering. So we do some measurements. To measure the waveforms. We capture the waveform, and so that we can choose a proper solution for that. Okay? So with the measurement, and we confirm which devices and what is the durations of the voltage sets, then we can do some the remedial activity here, and the remedial solutions here. And of course we can calculate the type of the voltage sets corrections, and then we correct the problem with changing some sensitive components to less voltage sensitive component, and then we identify the size of the loads to be protected. This one is using the protections of the voltage sets. So that means we can fine tune our setting at the relay there. And some possible voltage sets correction methods. So we have a lot of the methods as compared to the harmonics. So for the voltage sets, we have a ferro-resonant transformer, you have UPS as we have learned in the chapter 3, and a flywheel motor generator. Okay, so this is from flywheel, dynamic voltage restorer, and the static VAR compensator. These three are depends on the storage energy. That means they use the storage energy to top up the power that required during the voltage sets, just to correct back the voltage. And the sex proving transformer as well. And the ferro-resonant, as you can see here, so the voltage sets down to 30%. It can retain the voltage to mitigate using this technique. If it's more than this percentage, it is not it's not encouraged to use the ferro-resonant transformer. Okay, so as you can see here, the primary part you have one winding here, but at the secondary part you have two windings. One is for the power windings, the normal secondary winding, and another winding is just to store the energy during the necessary when it required the energy storage to correct back the voltage and the voltage sets, and then it will take the energy or the power from here. Okay, so this is another special thing of the ferro-resonant transformer. So it has two windings at the secondary. One is for the energy storage here, but the size is just up to about 25 kVA. It's just a small size only. And UPS, of course the UPS also it has the battery, the energy storage element, and so it will top up, it will inject a certain amount of the power just to correct back the voltage, especially the reactive power. So because the voltage is related much on the reactive power as compared to the active power. Okay? And flywheel motor generator also in the normal condition. So the motor will run, and it will store the kinetic energy, the kinetic energy at the flywheel here. Okay? Once you have the voltage set here, then the flywheel will automatically running, and it will deliver the stored energy here to correct back your voltage set. Okay? And same to the DVR. The DVR is using the power electronics to have the feedback. Let's say you have the control system here, and you have the feedback, and try to measure how much is the existing voltage, and it will top up, say, using by changing the VSC here, the voltage source converter, the voltage source converter, to top up the amount of the Q that is required to adjust back the voltage. And the static VAR compensator, as we see, as implied by the name, is the VAR. VAR means is the reactive power, But this type of the equipment or the corrector is just based on the static VAR compensator. I mean, this always give the certain amount of the VAR into the systems. And the stack proving transformer, finally, So this one is some sort like you have the tapping, tapping. So you have switch 1, 2 up to 7 in this case. In this case, so they mean, of course, it has the controller to measure what is the existing voltage, and then if you have the voltage sex, then of course it will switch to a certain switch here, a certain level of the switch. For example, if you require up to switch 3, then it will switch on the switch 3. So just to correct the voltage sex, but this application is up to 5 kVA only. Okay, finally we have the flicker analysis. So of course the flicker is the you can observe the flicker easily through your eyes, from the deviation of the lighting quality, and the lighting, especially from the lighting, you can easily detect the flicker. Okay, that means the flicker is due to the fluctuations of the supply voltage. So it is much related to the supply voltage, especially when you use the fluorescent lamp. So fluorescent lamp is one of the voltage sensitive devices, voltage sensitive equipment. Oh, sorry, is the devices. So voltage sensitive devices, then normally if your voltage, especially the incoming voltage, is fluctuating, then you can see the flicker. You can see the flicker. It's very obvious. Okay? So that's why the flicker is due to the fluctuation of the supply voltage. Okay? So what is the main source of the flicker? The main source of flicker are the large and fast variation of the industrial load, for example. Okay? So that means you have the load changes, very fast, very rapid load changes, and then it might have the flicker. It might have the flicker. Such as the arc furnace, you have the motor, rolling mills, and the welding machines, and as well as the boiler, which is in the large amount of the power. And the voltage flicker also is categorized by the variation of the voltage magnitudes in the range of 10% of the nominal voltage, and the frequency also. The frequency is very low. The frequency is very low. It's about 0.2 to 30 hertz only. It's like this one. If we are operating at 1 per unit, for example, the 1 per unit, okay, of course it will fluctuate to the high and to the low. So the lowest is up to 0.8, and the highest is up to 1.2, for example, in this case. So we have the different the voltage deviation, del V. So the del V, if we divide by our voltage, which is 1 per unit, then we can get this is 0.4. 0.4 divided by 1, then you have 0.4 per unit, or 40% of the deviations. Then of course in this case you can simply calculate the frequency. So the frequency you can calculate, let's say, for one cycle, for one cycles from here up to here. So from here up to here, so you can see what is the frequency here, from here to here. Okay, let's say this is 0.145, let's say 0.145 second, and this one is let's say about 0.03. Then you can calculate for the frequency. That means 0.145 minus 0.03. I mean you just 1 divide by this value just now, 1 over this value, then you can get the frequency. It's about 8.8 frequency, 8.8 hertz in this case, right? So of course if you have the problem of the flicker, so you can use the meter and to measure it like this one, and then of course this one is your the magnitude, that means the variation of the voltage. So in this case it is happen at this sampling time. Okay, so the magnitude is dropped up to maybe 0.085 here. Okay, and after that we just plot the frequency. Either you are using the Fourier series or other that can can that means can so-called the transfer, right, the time domain to the frequency domains. I mean, you can see at what frequency it is having the magnitude, higher magnitudes. So this is the flicker area, the flicker area. So normally it's less than our frequency, our operating frequency. Right. So with that, I think I have ended the chapter 4. Okay.